Welcome to the lecture number 29. So, we have been discussing about the gravity gradient satellite. So, we will continue with that. So, if you can recall that if a satellite is moving in an orbit around the earth. So, this is your earth and there is a satellite here in this place. So, that satellite we showed by maybe some oblate set or whatever it can be. Then we have radius vector to this point, which is the center of mass. This we have indicated by C, and this is C, which is center of mass, and this we denoted by R C. And then we took any mass in this body, which is the satellite here in this case. So, let us say this is the mass delta m or d m, and the radius vector to this point from here to here, this is rho. Okay. So, radius vector of this point from the center of the earth, this point, okay, from the center of the earth, then we have shown by r, where r we have written as R c plus rho. This is the radius vector of the particle d m. Okay. Then if you remember that we fixed the triad about this axis, this point, and which we have written as along this direction we took E O 3 cap, we have shown it by E O 3 cap. Along this direction we have shown by E O 1, and 2 is going into the page, which going into the page always we show it like this. This means you are looking at the back of the arrow. So, arrow is going inside, and therefore, you are looking at the back of the arrow. So, E 1, E 2 and E 3. So, this forms the right handed system. So, as you can see that this radius vector R c, this is the radius vector R c, it is corresponding unit vector we can write as E cap c, okay. And E cap c and this vector E O 3, they are related by E cap c, we can write this as E cap O, and here in this place we can write 3. So, this is the E 0, the system E 1 cap, E 2 cap and E 3 cap. These are zeros, small zeros shown here. This stands for the orbital reference frame, which we have discussed in the previous lecture. And then the body axis, its body axis system, it is oriented with respect to this orbital reference frame. So, I will not show it here, otherwise this figure will get totally destroyed. So, let me show it somewhere else, like if you have, this is your E O 3 cap, in this direction you have O 1, and going into the page. So, this is your orbital reference frame. So, with respect to this your body reference frame, it may be oriented arbitrarily, but again it will form a right handed triad. So, and this orientation, obviously this is a two dimensional figure on this page, it cannot be shown that correctly, but if you look like if I have this E 1 cap, E 2 cap, E 3 cap. So, instead of this place I am showing it here. So, we can show it something like this. Let us name this point as E cap B 1, then E cap B 2 and E cap B 3. So, this forms a right handed system, means the body axis system has already rotated with respect to the orbital axis system. Okay. So, with this then we wrote the force acting on this small particle, which is here in this point, d f equal to minus mu times d m, then r, which is the radius vector of this point from the center of the earth, divided by r magnitude whole cube. And therefore, the gravity gradient torque about this point, okay, which I am showing here by blue point. Okay. So, gravity gradient torque it is important to remember this gravity gradient point, because it is because of the variation of the gravity along the radius vector r. So, gravity gradient torque, if we show it by say we can show it by some tau or some any other notation we can use it, it is not a problem. So, let us say that we show it by tau. So, this will be rho cross d f, and therefore, this is minus sign will come here, rho cross d f equal to mu d m, r we can write as this is r c plus rho. So, r c plus rho and divided by r c plus rho magnitude whole cube. And if you see that this if we break this bracket, so this cross product rho cross will be 0, and this gets reduced to mu d m rho cross r c divided by r c plus rho whole cube. And if we integrate it over the whole body, that gives me tau. This is the gravity gradient torque. Gradient. So, this point is C here, gravity gradient torque about C, which is the center of mass of the satellite. Okay, one thing I will advise you, sometimes writing inadvertently some error will get introduced, because like here the minus sign is there. If I go to the next page, so automatically sometimes this error may introduce that instead of minus there it is plus, this minus sign is left, but later on it most of the time I have corrected it. So, just wait for, in the case you find that there is any error like this sign omission, or somewhere instead of if I remember in some place I have written something like a tilde dot, and then instead of this it should have been a tilde times a tilde dot transpose, something like this. Okay. So, this kind of error can get introduced while working. It is because of the attention getting from away from this place or going from one page to another page, this kind of problem can appear, but I correct it all the time. So, just keep tracking. Okay. So, if you find that somewhere some error is there, so go to the next page or whatever, you wait for some times, mostly because if the result does not match. So, I correct it, I go back and then correct it. So, we have here tau this equal to minus mu times rho cross R c divided by, this is the place where most often we do the mistake, copying from one page to another page. So, this is mu rho cross R c over the whole body, we have to integrate it. Okay. So, first of all we will determine this factor. As we can see, this R c plus rho whole cube, this can be written as, this is R c magnitude. So, this is R c rho dot R c plus rho 3 by 2. Because if I am taking a square term here, this is the dot product. So, this becomes a square and therefore, I must divide this 3 by 2, okay. And then break this bracket. So, this will be R c dot plus 2 times R c dot rho plus rho dot rho. This is R c square plus rho plus rho square, and if we take R c outside, so this becomes R c cube, and once we have taken this dot product here and written in this way. So, this mod sign we can remove it, this magnitude sign, and we can put a bracket here. So, R c cube 1 plus 2 R c dot rho divided by R c square plus now this term here, it is lying here in the denominator. So, if we take it, so we have to take it upside, like here in this place itself I will work and then transfer it here. So, 1 by R c plus rho whole cube, this quantity will be then R c minus 3 and then 1 plus 2 okay. And if we do the binomial approximation to the first order, so this will be minus 3 by 2 and then multiplied by 2. So, that gets cancelled out. So, this is 3 R c dot rho divided by R c square minus. So, these are the places where the mistake can occur. Okay. So, here once we are taking the binomial, just I wrote it plus, but it should be minus here. So, this is minus 3 by 2 rho square divided by R c square. Now, looking into this quantity, this rho can be of the order of, say, rho by R c, your satellite. In the case of the International Space Station, if we are considering, so in that case rho can be of the order of 100 meters. Okay. So, let us say this is of the order of 100 meters, and R c is the distance from the center of the earth to the center of mass of the satellite. So, that distance normally if you take the earth radius to be 6, this is around 6374 kilometers, 6374 kilometers, and to that you can add the altitude of the satellite. Let us say that it is in the 300 kilometers orbit. So, this becomes your RC, and then multiply it by 10 to the power 3 to convert into meters. So, you can observe from this place that what will be the order of this quantity. So, this quantity, and then once you square it. So, by squaring you are making it further small. So, therefore, this quantity is negligible. Okay. So, we can consider only this quantity here. If you look that look here in this place, RC, and here RC is also there. So, RC will magnitude by it cancels out, then we get rho by RC. So, again rho by RC it will be given by this. Okay. So, once we square this term, so this term becomes very small, but that is to the second order. This is, we call this term to of the first order term, and these are the higher order terms in RC and rho. Okay. So, this time here we could have written plus higher order terms, okay, plus higher order terms. So, this kind of terms we can ignore, okay. But if you are looking for a very precise calculation, then you should take into account, otherwise for getting into the physics these things should be ignored. Now, once we ignore this, so what we get, this tau equal to minus mu rho cross RC dm times this quantity we have to pick up from here. So, this is RC minus 3 1 minus 3 RC dot rho divided by RC square. Okay. This term from here to here we have picked up, and this term we have ignored. Now, this term we will take this rho on this side, and this RC will bring on this side. So, this minus sign can be absorbed in this, and therefore, this can be written as mu times, and one thing more, that this RC is integration over dm is just related to this rho. Okay. This is not depending on RC. Therefore, this RC can be taken outside. We can write it like this, okay. And then we have the rho, minus sign we are absorbing because we are flipping it these two quantities, these two vectors, and then thereafter write all these terms. So, here we have, similarly we can take here from this side the RC cube one minus 3 RC dot rho divided by RC square dm. So, this RC we have taken outside, cross we have taken outside, this rho is here, this term we have picked up from this place to this place, and this dm appears here in this place. So, in the next step, okay, we take this rho inside, and if we take it inside, so we can break it like this. This is rho dm minus 3 RC dot rho times rho by RCA square, and this also we can write here, this is dm. Okay. So, these are the two integration, and we know that rho dm, because rho is taken from the center of mass of the satellite. So, this quantity will be 0, as we have discussed earlier also, So, this quantity vanishes, this quantity will be equal to 0, and therefore, this gets reduced to mu R c by R c cube, then cross is here and 3 we can bring from this place to this place, and as we see this minus sign is present here, then R c dot rho by R c square. This R c square is there. So, we can take it here in this place, make it 5, and this R c square we can remove from this place. And finally, we need to process this. Okay. So, if you see, this is a scalar R c dot rho, this is a scalar and this is operating on. So, this R c is a vector which whose dot product you are taking with rho. Now, this quantity we need to work out. So, this is your tau. So, this previous one, this equation we have copied here in this place. Okay. Now, this particular equation it can be rewritten as 3 mu by R c phi R c cross, and if you look here in this place we can flip this. Okay. We can write this row, because this is a scalar, this whole thing. So, this row can be brought in front, and moreover if you look here. So, this is a dot product. So, it is a either it is in this place or this is in this place, it does not matter. So, we can change the order of this. So, if we change, we can write it like this, this is d m, and therefore, this can be simplified. So, we write this as 3 mu R c phi rho d m and dot R c, because this R c is not dependent on the integration. Okay. So, if it is not independent depending on the integration, it can be written outside. Now, from here we need to go back and look into what this quantity is. So, if you remember that the equation for the angular momentum, this is angular momentum, about the center of mass, we have written as rho cross. These things we have developed earlier while dealing with the rigid body dynamics. And then this we wrote as rho dot rho times omega minus if you remember this thing we have already worked out. Okay. So, in the dyadic notation, so this can be written as and we can rewrite this as Okay. While working with the rigid body dynamics, this equation we have written, and we know that this quantity ultimately we have tagged this as the inertia. So, if you want to write in the form of matrix, we can write it in the form of matrix. If we write in terms of the dyadic, we can also do that. So, from this place, this appears like here this quantity we have written as inertia dyadic, okay, from this place to this place. So, I double dot, okay, so H, this is the quantity H we have written. So, what is of interest here in this place? This is the I double bar, which is nothing but the inertia dyadic, inertia dyadic, and which we are writing as rho square E double bar minus rho rho. So, if we try to rearrange this, so this implies rho rho d m, rho rho d m, this quantity will be equal to rho square E double bar d m minus I double bar, and this can be written as rho square d m, and E double bar can be taken outside, because E double bar it is a vector. Okay. This is related to the it is a dyadic, and where it is the unit dyadic. This is the unit dyadic. Unit dyadic, how we have written E double bar, this quantity will be equal to E 1 cap, E 1 cap, E 2 cap, E 2 cap, and E 3 cap, E 3 cap. If you operate with this unit dyadic on any vector, that vector remains unchanged, as you can check it. So, copy it here in this place and take the dot product with omega, where omega is omega, this omega we can write as, let us write in the full form, omega 1 E 1 cap plus omega 2 E 2 cap plus omega 3 E 3 cap. Okay. So, if we take the dot product, we will see that this will result in omega. So, that was the thing that we have done this part, this omega we have written in terms of unit dyadic and this omega. Okay. And therefore, this is just a dyadic which is which is related to the reference frame, and it has nothing to do with the mass, and therefore, it can be taken outside. So, here this can be written as this minus this, and this result what we are getting here in this place, this quantity equal to this quantity can be inserted here in this point, and then the system can be solved. So, we have the gravity gradient torque, we have written as tau, this equal to, we need to copy it here, minus 3 mu by R c to the power 5, and then R c cross this quantity, and then dot R c. Okay. So, moreover we use the result that we have derived on the previous page. I mean this result we can use it we need to replace it. Okay. So, in that case this gets reduced to R c to the power 5 R c cross. Now, this part we have to replace. So, this is rho square d m E double bar minus I double bar, this is I double bar dot R c. E double bar dot R c. Now, we break this bracket and this is minus and then other part will be plus. So, this is 3 mu by R c to the power 5 R c cross this is R c cross I double bar dot R c. So, this is dot product of this R c with the unit dyadic. So, ultimately this will be nothing but R c. So, this quantity is nothing but R c. Okay. So, therefore, in the next step we can write this as 3 mu by R c to the power 5 R c cross R c plus and this is nothing but 0 because it is the cross product of the same vector. So, this part vanishes and what we get is 3 mu by R c to the power 5 R c cross I double bar dot R c. So, this is the gravity gradient torque equation. Okay. Now, look into this quantity. If we define R c equal to R c times E c cap. Okay. So, this equation can be reduced to, if we define where E c cap, this is the E c cap, this is the unit vector along R c. That implies that in this figure here R c vector is going from this point to this point. Okay. I hope it is visible on the board. Okay. This is visible through the cursor, it is going from this point to this point. So, R c E c cap is the unit vector along this direction itself, along this direction. Okay. Okay. So, if we insert this here in this place, so this tau, this gets reduced to 3 mu by R c 5 and here R c times E c cap cross I double bar dot R c times E c cap. So, this is your final equation, but still here if we look into this, this is expressed in terms of this E c vector. This is expressed in terms of this E c vector, which is going from this point to this point. But most of the time we work in terms of the body axis coordinate system, means we will be working in terms of this E1b, E2b and E3b. B tag stands for the body x, here B stands for body x, body axis, and then this O stands for orbital axis. Okay, so, we need to convert this in proper format. So, you can see that EO3, this vector EO3 which is shown here by this green, okay, and this vector, they are directed, they are obviously unit vectors, but they are directed opposite to each other. Okay. So, instead of using this R c, I can equally write in terms of EO3, okay, because they are the vector all along, these two vectors will be opposite to each other. Suppose the satellite, it moves from this place to this place, it comes here in this place. Okay. So, this is the center of mass, and then at that time your the direction of the E cap O3 will be like this, while the R c vector will be directed like this. So, this will be your E c cap direction. Okay. So, they are opposite to each other and they are of unit magnitude. So, if you are writing the whole thing here in terms of E c, so it is directly it is convenient to express this as 3 mu R c cube, and instead of this we can have here with minus E cap O3 cross minus sign, this cancels out. So, you will question that what to do for this. This I double bar, it is written in terms of, if you go and look into the previous page, it is written in terms of rho. Okay. If you look into this I double bar, this is written in terms of rho and this rho vector, rho square and rho vector. Okay. And this is a unit dyadic. Okay. So, rho vector as we have changed it to from the R c notation to this notation. So, it says that we can express everything in terms of this EO cap, or otherwise we can go very systematically using the matrix method and change from one reference frame to other reference frame. Like first assuming that this R c is described in the inertial reference frame. Okay. Therefore, this E cap c we need to convert it from this frame to the orbital frame. Okay. We will need to convert it from E c frame to the orbital frame. So, this will be little long, I can do it here. Okay, that I will do, but I will do it in the next class. For the time being, let me finish this. So, this can be, this is basically here, if you are writing in terms of the R c, you were using this R c vector, for which you have replaced it by the E c cap, the unit vector. So, that means from here we have then transition to the orbital reference frame vector, which is along the z direction of the orbital frame, this part. Okay. So, therefore, this can be expressed in the, this is basically expressed in the orbital reference frame, and once we go for this one, this particular one, see here this dot product is there, this is dot product, this is cross product, we have to be very careful. Because this system is I am not able to show you properly, because this is on the screen, computer screen. If it is a page paper system, then I could have easily shown you everything. So, if you look here in this place, this I double bar vector is this dyadic is there, which we are telling it as the inertia dyadic. So, this inertia dyadic is currently we are expressing in terms of orbital reference frame vectors. Here it is expressed in the terms of these vectors, okay, E 2 cap, E 3 cap. And if you do not want to do this, then come from start from this E c vector, and assuming that this E c vector was in the inertial frame. So, we can go to the orbital frame system, and from orbital then we have to finally go to the body frame system. But here in this case it so happened that E c and E 3, this E O 3 cap, they were directed opposite to each other. So, we have been able to replace, but thereafter going to the body frame we cannot do it so conveniently, and we need to do certain transformation. So, I will keep this equation for the time being here, and I have something more to tell you. So, I feel that time is over for this lecture. So, we will continue here. So, what we have concluded today, that this is my final equation, but still not in the format we want. Finally, this is the final equation. Okay. So, I will stop this lecture here. Thank you very much for listening. We will continue here in the next lecture.